So real quick here, tell me read this problem. Tell me in this problem, what are they? You got to kind of think about this a little bit, right? What quantity are we going to optimize here? Minimize or maximize? You tell me which one in order to answer this question. And they want minimum weight, but they don't really tell you anything about weight here, right? So what's going to be our proxy for weight here? We have to find something else that's going to stand in for that, right? Surface area. Everybody see that? Right? If the steel is all the same thickness, then the surface area is going to be equivalent to weight here, isn't it? What we could say is this: when we minimize surface area, we're minimizing weight because the steel it's uniform steel, right? Okay, does that make sense? Okay, all right. So sometimes you got to kind of be, and we've had a couple like this now where you just got to find an easier problem to solve that has the same answer, right? Okay. How about something like this? A little kinematics here. Do a little physics. So they give us the height of a projectile that's launched vertically. They give us the height function. S is height as a function of time, right? Okay, where t is in seconds. So find the object's velocity at t equals 3. We want to find its maximum height and when that occurs, and its velocity when the height is 0. Okay? All right, so it's been a little while since we've done one of these. What do we got to do? How do we find velocity? Yeah, right. Remember, velocity is the derivative of position. In this case, position is just height, right? It's all vertical. So velocity is the derivative of position with respect to time. So our velocity function is just equal to s prime of t, which would be what? Okay, makes sense. And now that we've got our velocity function, we can answer that first part. So what's the velocity at t equals 3? Well, that's just v of 3, whatever we get when we plug 3 in, right? So this first part, that's just going to be v of 3, and it's just going to equal some number, right? We don't have to even find out. It's going to be something. What's its maximum height? Okay, so how are we going to come up with maximum height here? In the past, we did problems like this in Algebra 2, but at the time we didn't know any calculus, and so we had to just take advantage of the fact that we knew this was a parabola and find the coordinates of its vertex, right? We knew that this thing opened down because a was negative, and so we knew that the vertex was going to be a maximum. We can do this much more easily now, though, in calculus. What's going to correspond when we talk in physics? We talk about events, right? Events happen at a certain place at a certain time. So the event that we're interested in here is our frame in the movie, right? Is the frame where this thing gets to its maximum height. What's interesting or important about that point? Somebody raise your hand here. What do you think? Say it again. Who was saying it? Okay, velocity. Okay, everybody get that? Velocity 0. Right, that's what's going to be the important. That correlates to maximum height, doesn't it? The velocity is positive on the way up, it's negative on the way down. The transition between positive up and negative down would be when it's at 0. So we know that this spot right here is going to be when v equals 0. So we'll just take our velocity function and set it equal to 0 and solve. Okay. Here's our velocity function. If we set that equal to 0, I can just add the 32 to one side, divide by 32, right? and I get t equals 48 over 32. And what is that? 3 halves? So 1.5 seconds, right? Okay, so we know. So we know that's when it reaches maximum height. What's its velocity when s equals 0? Okay, well, when is s equal to 0? When it's on the ground, okay. So we need to, but they don't tell us that directly. How are we going to find out? What are these kinematic functions all functions of? We didn't calculate acceleration, but we could have. They're all functions of what? Time, right? Time is the common parameter here. We call the system of parametric equations, right? Because they're all functions of a single thing, which is t, okay? So yeah, we've got to be able to know what time is. We got to be able to find that frame in our video based on the time, right? They're all time stamped at the bottom of the video. We got to find the one that's got the time that causes this to happen, causes the height to be 0. So how would we do that, Seth? Say it again. Right, so we're going to set the original function, the height function. We want to ask the math gods or the physics gods, I don't know which one's which. We're going to ask them when the height is 0 by just setting height equal to 0 and solving. Right, so this last one then, velocity when s equals 0. How do I do that? I don't know how I do that. I'm so tricky, but I don't know how I'm so tricky. Okay, it's velocity when s equals 0. We're just going to set this function equal to 0. And solve, right? Okay, let's do that real quick. So how could we, this is good practice, solving quadratics. So what should we do to solve that? What do we do first here? Any ideas? Go ahead. Yeah, were you saying something, Johan? Okay, and we could, because we're solving an equation here, we could even just, if we want to, we could even just divide both sides by a constant. What would that be in this case? 4, it looks like. -4. Divide both sides by -4. And the negative is key, right? Because when we solve a quadratic equation in standard form, remember, we always want a to be positive, right? So if it's negative, we're going to change that. Multiply both sides, multiply or divide both sides by a negative. So that's going to give us 4t squared minus 12t minus 9 equals 0. Okay, how can we, this is good review. There's the equation we're solving. What's the easiest way to solve that one? What do you think? Okay, well, we could see, right? We can solve this thing by factoring if we can find magic numbers, if they're easy to find. So let's see, magic numbers would have to multiply to -36, right? They have to multiply to AC. And they have to add to -12. So we'd have to have a negative and a positive, right? And the negative would have to be 12 bigger than the positive. Do those numbers exist? I don't think they exist, do they? Right? 18, 2, no, that's not going to work. So there are no magic numbers. So we'd have to do something else. So we'd probably just use quadratic formula on this, right? So we get t equals, you guys remember the song? So with -b, that's 12 plus or minus the square root of b squared. If I square a negative, I don't square a negative, I just square the positive, so I don't make a mistake. So that's going to give me 12 squared minus 4 times 4 times negative 9 all over 8, 2a. All right, so what's that going to give us? What do we get inside here? 144 plus, I get a negative times a negative, so I get a plus 144. So that's 288, right? So we'd end up with 12 radical 2. That is right, isn't it? 16, yeah, that's right. All divided by 8. So we're going to end up with 3 halves plus or minus 3 radical 2 over 2, right? So we're going to get, if we turn those into decimals, we're going to get one that's kind of a small negative and one that's a bigger positive. Does that make sense? Right? Which one do we probably want in the context of this problem? Probably want the positive one. We probably want the 3 halves plus 3 radical 2 over 2, right? What's that roughly equal to? Somebody got a calculator handy? Say it again. 4.854. Okay, so about 4.85 seconds. What is 3 halves minus 3 radical 2 over 2? Change that to a minus, Ember. What do you get for the other one? Okay, negative 1.854, 1.85. Okay, so this is the one we probably want. What's the meaning of this other one? You remember we talked about one like this in class? Yeah, if you reverse time, this thing started at a height of, if I let t equal 0, look what we can do here. If I let t equal 0, s of 0, that's the initial height of this thing, right? That term's going to go to 0, that term's going to go to 0, and so I just get 36. So this thing started off at a height of 36 whatever units, feet, I guess, right? Height of 36 feet being shot up into the air, and then it turned around and came down. So if we had run time backwards a little bit, in order for the projectile to be at a point that's 36 feet above the ground with my initial velocity that I had, it would have had to have started about 1.85 seconds before the first frame of the movie. That's how long it would have taken to rise up to 36 feet with the exact initial conditions that this object had at the beginning of this problem. Okay, so is it important? Not really. We don't want it for this problem, but it does. Once again, the physics gods and the math gods, they give us important information, even sometimes we don't need it, right? Questions on that? Well, good with that stuff? Okay. Okay, this is a pretty good one. There's a lot of good stuff that comes out of this. You can do, I'm not going to do it now, but maybe at the end of the year, if we have a little extra time with something, you can use this to do some pretty cool physics. You can do that. You can use this kind of a problem to do some refraction problems. Like if you have light that's going from one medium to another and it's refracted, that's how glasses work, and that's how light, when light is bent. A good example of that would be if you're looking in the water, and here's a good physics question for you. If you're looking in the water, you're stranded on a desert island. Try to make this practical for you. You've fashioned a spear and you're getting pretty hungry and you got to spear this fish. Okay, you're looking in the water and you see the fish there. Do you want to aim right at the fish with the spear? Where do you aim? You aim below it a little bit, don't you? If you're at an angle, right? If you're straight up, then you just aim right at the thing. But if you're at an angle, you got to aim a little bit below. How come? Because of refraction, because the light is bent by the water a little bit, by the boundary between the water and the air. The light's refracted. Okay, so you can use this kind of a problem exactly to explain how light is refracted with slightly different conditions, but it's the same calculus. All right, so this might seem like an odd problem, but it's really good. So a hunter's at a point along a riverbank. He wants to get to his cabin. So there's his cabin, there's the hunter. Here's the river, I guess, right? I'll draw the river in for you. There's the river, right? He wants to get to his cabin. It's 4 miles north and 10 miles west of where he is, okay? So what's he going to have to decide here? If he wants to get there as quickly as possible, he can travel 5 miles per hour along the river, but only 2 miles per hour on average over the rocky land. So if he wants to get there as quickly as possible, what kind of a decision does he have to make? Say it again. Yeah, so he's going to go, where does he leave the river and strike off across the land, right? This could be a really important situation, and so it's a good thing this guy knows calculus, and he can sit down and figure this out. Yeah. All right, so let's figure this out here. We got a picture, right? We need to probably add a variable to our picture. What's the thing that we can vary here? Okay, so right, but river? Is there maybe a better one? Distance along the river? He can decide when he chooses, at what point he chooses to leave the river and head in a straight line towards his cabin, right? So if that's the thing that this person can vary, then that's the variable, right? So x is this distance right here, we'll say. Okay, we got a variable, we got a picture. What's next? What's our next step in optimization problems? Think about your little list. You can get it out if you want to. What's your little list tell you? The equation. Good. So we need the optimization. We need the objective function or the primary equation, whatever you want to call it, right? It's in our book, the online stuff, they always call it the objective function. So what is the thing that we're trying to minimize in this case? Time. Okay, so we got to come up with a function for time. X is written in terms of distance, right? So we've got to relate time and distance here. How are time and distance related if we're given information about speed? How does speed relate time and distance? Okay, so speed is equal to distance over time, right? Everybody agree? Okay. And instead of speed, I'm going to call it V for velocity. How about, just so it's easier to see. So velocity equals distance over time. We're trying to minimize time, so we want to solve that for t, right? How do I solve that for t? Well, you remember this little trick? I know I showed this to you. You may not remember it. But if I have a proportionality, I can always exchange things diagonally. That's a cool little trick, right? So if I have something like this, if I have a over b equals c over d, if I want to solve for b, for example, a really easy way to do this, well, maybe in this case, I wouldn't always be solving for b, but sometimes I want to rewrite this proportion in a way it could be various reasons. I'm solving for something or I'm looking for a different ratio. Rather than having to cross multiply and divide, I can always just do this. I can just exchange those things. So that's equivalent to d over b equals c over a, right? You can exchange diagonally in a proportion. So in this case, I could exchange the t and the v, couldn't I? Because the v is over 1, right? So t equals d over v. Okay, that looks a little better for us, right? So our time function is going to be distance traveled divided by velocity. What do you think here? Any ideas? Aren't there two distinct parts to this journey, though? Right? There's the time on the time he's going to spend on the river and the time he's going to spend on the land, right? Okay, so how could maybe I could set up a time function. This is going to be t as a function of ultimately probably x, right? Because that's the thing that we can choose where we leave the river. But we can split it into two parts. We can have the time along the river plus the time across the land. Call them t sub r and t sub l. So what's going to be the time along the river then? If we're defining the distance that he's traveling along the river as x, what's going to be the time along the river if this is our relationship? Okay, so the distance he's traveling, the d is going to be replaced by an x. The speed or the velocity on the river is 5, right? Everybody see that? So we're going to get x over 5. How about the time along the land? Well, what's the distance? We need to know what that distance is. Okay, we've defined a variable x. Can we write this distance here in terms of, and here we'll do it this way. So there's d sub l, right? Can we define that in terms of x? We got a right triangle, don't we? If I have a right triangle, that helps a lot because now I can use Pythagorean theorem. So I know this side is 4, this leg is 4, this is the hypotenuse, isn't it? What's the length of that leg? Oh, okay, 10 minus x, right? So now we got it, right? By Pythagorean theorem, the distance, the hypotenuse would just be the square root of 4 squared plus the quantity x minus 10 squared. Okay, so we get square root 16 plus 10 minus x. Squared all over my speed there, which is 2 miles per hour. Okay, make sense? That's good. I've got a time as a function of a single variable, so this is t of x. We can do calculus on that. We need the domain. So what are the logical values here that we could consider for our domain? The values of x that make sense in the context of this problem. What do you think? Say it again. Well, I mean, you could. The river flows forever, right? We'll say it's just a straight stretch of river. So below 0, if x is negative, if we're defining how far he's moving along the river as x, I mean, he could go backwards, but that's not very smart, is it? Right? We can rule those out because we know those are going to be bad solutions, right? Those aren't going to work. So 0 is probably our lower limit for our domain. What's the upper limit? 10. We wouldn't want to overshoot and then have to backtrack. That wouldn't make sense, right? So 0 to 10. Okay, so now we just have to do some calculus. We can flip the switch and just go into calc mode here, and then we don't have to even think about the problem for a while, about the context of the problem. So let's simplify this. We could simplify this stuff under the radical. So that's going to give us, what, x squared minus 20x plus 100 inside, plus 116. All right. So we got to do some calculus. We got to find a first derivative. Are we probably going to want to do a second derivative on this one? I don't think so, right? We've got radicals in this. It's going to be a mess. We'll just use the first derivative test. Take the first derivative and find critical numbers, and probably just use the first derivative test to see what those are, what our critical numbers are. All right, so let's take our derivative. Derivative of the first term. What's the derivative of the first term? Derivative of x over 5. 1/5, right? That's just a 1/5 times x, so I just get 1/5. Okay, this one's kind of nasty. This is going to be a chain rule one, right? But what's a square root? How do we think of a square root here? 1/2 power. Okay, so really, we don't have to write it this way, but really what we've got here is the quantity x squared minus 20x plus 116 to the 1/2. So we've got to do chain rule stuff, right? So the derivative of hand to the 1/2 is what? 1/2 hand to the negative 1/2, which really just, what's negative 1/2 mean? Negative 1/2 power. The negative does what? Puts it on the bottom, and the 1/2 makes it a square root, right? So the 1/2, we've already got a 2 there. We can combine that with the 1/2. So we're going to get a 1/4. We'll put the 4 on the bottom, how about? We said we got a 1/2 times 1/2 is 1/4. Hand to the minus 1/2. So this goes on the bottom. Okay, now we got to go inside the derivative. So the derivative of hand is what? 2x minus 20. So on top we'd have a 2x minus 20. Does that make sense? Got our two layers there. Okay, and we just put them in one big fraction. So we want to find out where that's equal to 0. Okay, so we could just maybe subtract this 1/5 to the other side. And we get, we could do one other thing too. What if I factored out a 2 and divided by 2 here? So we make that a 2 and that a 10. Factor a 2 out and cancel. So we get x minus 10 over 2 times my big square root equals negative 1/5. Now what? Got to solve that thing. What am I going to do? Kind of, and sort of, you got to want to really, I mean, you can just start cranking through algebra steps, but sometimes it's good to pause and just think ahead a little bit. What do you see as being the problem in this? The problematic part of this problem? Okay, yeah, we got a square root there, don't we? So we're solving a radical equation. How do we solve radical equations? Thinking back to algebra 2. What do we do? Yeah, good. So you isolate the radical, right? And then I square both sides to undo the radical. Okay, and there's some issues we've got to consider when we square both sides. We'll get there in a second. So first of all, let's isolate this guy. So if I cross multiply, I get. I'm going to go ahead and do that. Well, we'll do this. So I get negative 2 times the square root of x squared minus 20x plus 116 equals, this cross product's going to give me 5x minus 50, okay? All right, I could square both sides now, right? What's the danger? Well, it's not a danger, we have to do this, but when I square both sides, what do I have to be careful of? Not exactly. Let me give you a simpler example real quick. So what if we had something like this? What if I make a real simple one. What if I had the square root of x plus 1 equals negative 4? Okay, if I solve that by squaring both sides, look what happens. If I square both sides, I'm going to get x plus 1 equals 16. Subtract 1, so I get x equals 15. We're all good, right? No, if I plug 15 back into the problem, into my original equation before I squared both sides, what's that give me? That gives me the square root of 15 plus 1, which is the square root of 16, equals -4. That's not true. Okay. So the danger is when you square both sides of any equation, there's the potential for introducing extraneous solutions, right? So we've got to always be sure that we check all of our answers. By checking our answers, we mean that we're going to evaluate the function before we squared both sides and see that they work before we took that step, okay? All right, so now if I square both sides, that's going to give me 4. I can square the -2, so I get 4 times the quantity x squared minus 20x plus 116 equals, if I square that out, why don't I pull the 5 out front? I'm going to rewrite this as 5 times the quantity x minus 10 when I square it. So that's going to give me 25 times x minus 10 quantity squared, which would just be x squared minus 20x plus 100, right? Everybody agree? So far, so good? Okay. I'm going to go to the next page. I'm running out of space here. Okay, so if I distribute, I'm going to get 4x squared minus 80x plus 464 equals 25x squared minus 500x plus 2500. So I push everything to one side, push everything over here, right? I'm going to end up with a positive x squared. If I add 80x, I'm going to get minus 420x. If I subtract 464, I get 2. Well, what am I going to get here? No, I'm going to get 1. Oh, no, I'm not. I'm going to get 2. I'm going to get 2032. 30. Oh, it's not 32. 2036. And all that's equal to 0. Okay, well, we're not going to want to solve that by factoring or anything. Let's just throw this into quadratic formula, and let's even, for the sake of brevity here, let's cheat and use Desmos. That's when you're a teacher, you have those privileges. You can cheat anytime you want to. Yes, did I make a mistake?
21x instead of just x.
Oh, you're right. 21x squared. Yep. Thank you. Okay, good. Can we do, no, doesn't look like we can. No, we'll just graph it. All right, 21x squared. If we look at this graph, well, there's 2 solutions. How many real solutions could this have at most? This equation? 2. It's quadratic, right? So we found them both. 8.254 and 11.746. Okay, we can try both of those, but do I even really need to try the 11 one? How come? It's not in our domain. That one I can almost guarantee is going to be extraneous. That one's probably not going to work. If we have time, we're probably going to run out of time, but if we have time, we'll show that. Oops, I could do it. But we do need to try the 8.254. We got to go back and make sure that that works in our equation that we had set up. Here's our equation right here. There's the easiest form of our equation. So if I plug in 8.254, is that going to give me a negative number on both sides? Okay. If I plug it in on the left side, 8.254, I'm definitely going to get a positive number under the radical, right? Because it's a little bigger than 8. Does that make sense? If it were 8 times negative 20 would be negative 160. 8 squared is 64 plus 116. That's bigger than negative 160, right? So I'm going to get a positive number under the radical there. I'm going to get a negative on this side. And over here, I'm going to get 5 times something. That's going to be less than 50, isn't it? Right? And so I'm going to end up getting, we can plug it in and just show it, but I don't want to waste time. That one's going to work. I'm going to get the right stuff on both sides. If I plug in the other one, though, you can already see if I plug in 11.7 something, that's not going to work, right? I'm going to end up with, on this side, over here, I'm going to end up getting a number that's going to be, it's going to blow up, first of all, because it's negative inside the radical. I'm almost positive. Let's check it. Right, and so we're going to get, oh, hold it, hang on. So we're going to get, well, let's just show it. I just want to quickly just reinforce this by showing that you got to be really careful when you square both sides. So let's just evaluate these. I'll just set up functions for both sides, and then I'll just plug values in. So f of x will be the left side. Okay, so there's the left side of the equation. Here's the right side of the equation. We'll call it g of x. And this is where Desmos, it makes it really easy to evaluate stuff. This is really handy. Okay, now we can just plug in our values. One of them was, what was it, 8 point, what was it again? Write these down on paper, somebody. We got, oh, that's the wrong problem. There it is. 8.254, okay, write that down, and 11.746. Okay, so if I plug those into my function, f of 8.254 gives me that, okay? G of 8.254, that's the right side, gives me the same thing, right? Just rounded. And why isn't it exact? Because that's a rounded answer, right? Okay, well, if we try 11 point what? Say it again, 746, okay, 11.746. On both sides, look what happens. I get one negative and one positive, so that's extraneous. So we can toss that one, which we knew we could anyway, and we got our answer, 8.73 miles. Good stuff, huh? And he probably better be pretty good at calculus if he's going to do that fast enough to make it work for him, but